Well, welcome. Do you hear me? Welcome everybody to the second day of this Poisson 2022 conference. So these are the CSIC headquarters. So CSIC is the Spanish National Research Council, and we're going to have the lectures here for the rest of the week. So today, a few practical announcements. So to have lunch, speakers can go to Residencia de Estudiantes, and the rest of us can go to the cafeteria of CSIC, which is, so you leave here and turn left again, and there is a big cafeteria there. You can have a menu there, it's fine. And also there are other options in Maria de Molina in case you want that. And besides that, just because it's complicated, let me mention this, that the toilets are on the sides. Okay, they are difficult to find. And that's it. I give the word to the chair, which is Joaquim Brugués.
Thank you very much. A very short reminder for anyone who's connected on Zoom. Feel free to ask your questions in the comments, and at the end of the talk, we will ask them to the speaker at every talk. Having said that, it is my pleasure to introduce Marius Crainic from University of Utrecht. And he is talking about the Ambrose-Singer theorem and Lie brackets.
Yeah, well, it is a pleasure to be here. So thank you very much for the opportunity to speak here. And I'm very sorry for the last moment change of title. It seems I'm becoming a specialist in changing my titles. I was supposed to talk about construction of symplectic foliations. So that's some very recent work with my colleague Gilles Cavalcanti. So for those which are interested, just watch the archive. The paper will be on the archive next week. Anyway, I decided to change my title when one of my students reacted, seeing the title of my talk, not symplectic foliations again. Well, I'm kind of kidding. No, I thought this was actually, I was very much in doubt what to choose. I mean, usually it's nice to have more research-oriented talks, but I thought this would be a nice opportunity to honor the memory of Kirill Mackenzie, who passed away since the last physical meeting in Poisson. And he has been someone who influenced many of us in many different ways. And at least in my case, I was quite a lot influenced by him, and also it's partly due to him that I moved towards the community of Poisson geometry. He was visiting somebody in Utrecht around 2000, and we got to talk to each other over a beer in the Jan Primus cafe next to the Outhof in Utrecht. And I think that's the way I really got influenced by Kirill, by talking to him. So sometimes when interacting with other people, they would say, well, it's so hard to read his papers. And I always say, no, go and talk to him. He has a very nice vision, and someone will learn some very simple but fundamental ideas from him. And that was certainly the case for me. So that's how I got into even groupoids, algebroids. I learned about Van Ness map and the relevance to the integrability problem. I even wrote a paper after that turned out to be very useful. So somehow that's all due to that beer that we had in the Jan Primus cafe in Utrecht. So my aim here is somehow to give some instances of the simple ideas that Kirill was playing with. So I don't claim anything new, but my aim is, I will be happy if some of you would say at the end, well, I knew this, but I didn't think about it this way. Or, well, I know this from Poisson geometry, I didn't realize that's also the case even for Ambrose-Singer. So that would be somehow the purpose of my talk. Okay, so let me just a summary of Mackenzie's word, what I call Mackenzie's word. So that's related to transitive groupoids and algebroids. So in his view, when he says principal bundles, he thinks about transitive groupoids. And I think for a long time when he said groupoids, he thought about principal bundles. So the correspondence goes via the gauge construction of a transitive groupoid associated to a principal bundle. So transitive groupoids have associated transitive algebroids that you think of as Atiyah sequences. So there's the analog of the Atiyah sequence for principal bundles that is used to interpret connections as splittings on the right of these Atiyah sequences. And so that the curvature appears as the failure of H to preserve Lie brackets. So connections would correspond to H, and the failure to preserve the Lie brackets, that's precisely the curvature of that connection. And we also learned, that was not that well known at that time, the integrability of abstract Atiyah sequences, the question of whether such a sequence of whether a transitive Lie algebroid comes from a groupoid. He found out a criteria involving some type of discreteness, a hidden discreteness in his description of certain second homology classes related to the curvature. So that's something that we discovered later on, and actually now that I think nobody went to prove that what we found is the same as what Mackenzie has. Of course, it's the same. It's the same, but it would be nice if somebody would write down a proof. I'm not aware of any proof being written down. Okay, so that's what I have in the back of my mind. And I'm going to look at the classical Ambrose-Singer, put the algebroid picture in the discussion, and discuss holonomy from the point of view of holonomy groupoids. So for the classical Ambrose-Singer, I start with a fibration over a manifold. It could be a principal bundle, it could be a vector bundle, or more generally just a fibration. Think about it as a surjective submersion. And I start with an Ereshmar connection, by which I mean a complement to the vertical part of the tangent bundle of N. Or equivalently, this operation of associating horizontal lifts, right? So for any point, for any vector in the base, there is a unique vector up there, which comes from H and projects back to the given vector. And I'm going to make the overall assumption that the connection is complete, which is automatic if the map is proper, or if N is a principal bundle. It's not always the case, in the sense that there are interesting connections which are not complete, but for the purpose of the talk, it's okay to assume the connection to be complete. Okay, and then associated to can then talk about parallel transport along paths in the base M. So I call it T tau gamma, which moves from between the fibers of the bundle, right, which sends a point above gamma of 0 to the endpoint of the lift, of the horizontal lift of gamma up to N. Right? So you have the path down in M, and you look at the lift. So of course the lift has to project down to d gamma over dt, which is horizontal. So if you see if it's horizontal, it means precisely that it has to be, the derivatives has to be the horizontal lift of the derivative of the base path. So it's a solution of this ODE with initial condition. And the completeness means that the solution exists for all t in the whole interval 0, 1. Right, so you have holonomy along foliations. Yeah, this is basic material, right? And then at each point in M, you have associated to the connection the holonomy group at the point, right, where you put all these holonomy transformations done along loops inside M. Then if you only use contractible loops, you get the reduced holonomy group. And these are all groups of diffeomorphisms acting on the fiber above the point X. Right? So these are the holonomy of the connections. And the Ambrose-Singer theorem describes these groups infinitesimally. So one has to make sense of the holonomy Lie algebras, and for that use the curvature of the connection, right? The failure of the connection viewed as a splitting to preserve the Lie brackets. Now you look at the expressions given by the curvature at the points of that point. These elements will be elements in the vertical tangent space of n, right? If you project down to M, these, you see, they all go to the bracket of x, y, both terms. So they will cancel, so you go to 0. So you see you get all these expressions at the point x will be tangent to the fiber. So you get vector fields on the fiber of nx. The only problem, let's say, is that if you start moving now from fiber to fiber via parallel transport, right? So you have the parallel transport to move from fiber to fiber. These subspaces may change, right? So this is not invariant. So what you do to build a holonomy Lie algebra, which is a subalgebra of vector fields on the fiber nx, you start transporting all these subspaces. So right, if you have a path gamma which starts at x, you do look at the subspace at the endpoint and you transport it back at x, right? So in this way you force your subspaces to become invariant. So you take the linear span of all that, and that's the holonomy Lie algebra of the connection at the point x, denoted whole x age. And now it depends a bit on the assumptions you make, but Ambrose-Singer type of theorems, which you usually see for principal bundles or vector bundles, here it's a version that I stated here. So assuming that this holonomy, oh, that's uncalled for. So assuming that these holonomy Lie algebras, right? So these are Lie algebra vector fields on the fiber, right? So they in principle can be very big. So if these holonomy Lie algebras are finite dimensional, then the holonomy groups is a Lie group. The reduced one is the identity component. The holonomy Lie algebra is the Lie algebra of that. Then the bundle you started with, you are interested in, will be induced by a principal bundle with respect to this group, holonomy group, right? So if you have a principal bundle, any principal bundle, if you have the group acts on space, you can attach that space as a fiber, and that's the construction here. So n is obtained by attaching the fiber nx to the principal bundle via the holonomy group. And then, of course, also the age will be induced by a principal bundle connection on P. Okay. Maybe I'm going too slow. So what happens is that intuitively one still has an Atiyah sequence like you have for principal bundles. It's like a sequence of vector bundles over M. One just has to be careful that these are not quite finite dimensional smooth vector bundles. So that's why I'm saying it's intuitively. Right? So just that the objects may be infinite dimensional. For instance, the fiber of xv at the point x are the vector fields tangent to the fiber of nx. So it's better to describe these at the level of space of sections over M, which becomes vertical vector fields on n, goes to projectable vector fields on N and goes to vector fields on M. So this is like the Atiyah sequence for a principal bundle. It's just that there are some technical problems with making sets of these as smooth finite dimensional objects. Okay, so now we can try to solve that problem by bringing Lie algebroids in. And actually, there is a leading question, and that's one of the main messages here. Really, the question to ask here is, can I find groupoids over M that act on N in a way that is compatible with the connection? So I have N, I'm going to draw it like this, goes to M. So I'm looking here for groupoids or algebroids or whatever, which act on N, and which are the best possible ones. I mean, there are some trivial ones, and you go in the other direction to find the best possible ones. So some of the message is that if you start with this question, you should discover the construction from Ambrose-Singer and maybe a bit more. And that's the proposition that this condition that you've seen on the holonomy Lie algebra being infinite dimensional, it's actually equivalent to the existence of a Lie algebroid over M, together with a nice or free action of the Lie algebroid on N, which is horizontal. So horizontal meaning that if I take A vectors, so elements in A, and I look at vectors on the corresponding infinitesimal vectors on N, they are horizontal. So it acts through horizontal vector fields. And moreover, in this case, you do find the smallest Lie algebroid which has these properties. And if you look, right, for any Lie algebroid, you can look at the isotropy Lie algebras. If you look at the isotropy Lie algebras of AH, you discover precisely the isotropy Lie algebras that I described before with the curvature and parallel transport and taking the linear span, right? So that's kind of nice. And this is really the important question, right? Fine, so that's something we've been doing in Poisson geometry more and more often recently. You have usually like symplectic realizations, and you try to find the best groupoids which act on them. So it's the same kind of question, but this is just a much more baby version. I'll try to come back to that a bit later. And let's see how these So from the proof, the interesting part is to see, right, starting from the sequence you have, so starting from your bundle, how the existence of this Lie algebroid forces the finite dimensionality of the holonomy Lie algebras, right? So forget about Ambrose-Singer for now. So I'm putting in blue the extra information that we have from the Lie algebroid, right? So we have the Lie algebroid, we have this isotropy bundle of the Lie algebroid, which is the kernel of the anchor map. We have the infinitesimal action, right, which takes sections of A into vector fields on N. So I call that A, that's the action. And that restricts on the kernel of these maps as an action of the bundle of Lie algebras vertically. Right, so that's like a bundle map, right? Meaning that each point X in M, you have a map from the Lie algebra at the point X to vector fields on the fiber. And now we're going to use this blue information, right? So H will land in gamma of A. So since H, I'm not very good with this. Since H lands in this gamma of A, and gamma of A is involutive, the curvature, which uses H and brackets, will still land, lands in GX, not just in the kernel of this map, but in the kernel of this map, right? So when you look at the curvature expressions, they will land inside gamma of G. So that's where the curvatures will land if you have the algebroid. Then also something that you have for any transitive Lie algebroid, if you have such a splitting, you have an induced connection, classical connection on this bundle of Lie algebras, right? Simply by using the bracket with the horizontal lifts. And that defines a connection on this bundle of Lie algebras G, the isotropy bundle of the Lie algebroid. And it has parallel transport to move from fiber to fibers. And if you look at the construction of parallel transport, you see that while these isotropy Lie algebras sit inside vector fields on the fibers, of course, now it's tempting to compare it with the parallel transport we used before, induced by the connection, by the original connection we started with. And you see that these actually coincide, right? So you see the curvature expression land in Gx, and this parallel transport is the parallel transport for the canonical connection on G, so that it preserves the G's. So altogether, the holonomy will be inside the isotropy bundle of the Lie algebroid. So if you have a nice finite dimensional Lie algebroid, the isotropy should be finite dimensional, so the holonomy algebras have to be finite dimensional. And also conversely, I mean, you just read off, I mean, now here it's tautological how to cook up the algebroid via sections by using the splitting. So that's, I hope, gives you a good idea of some of the relevance of these algebroid and Atiyah algebroids to the discussion of holonomy. And then using this AH, so this algebroid, the smallest algebroid which acts on n in a free and horizontal n, you can try to integrate it, and it is integrable. So you can integrate AH to a groupoid, GH over M, and the infinitesimal action A will integrate to an action of this groupoid GH. This is the fundamental groupoid of AH. So arrows, I mean, this is constructing from the algebroid by using paths in the algebroid and taking homotopy classes, and then the action of GH on N is by parallel transport along A paths. But one example of parallel transport is if you use the obvious horizontal A paths, right? So if you have a path down in M, there is an obvious on the fiber of N and about X, then the image of that is precisely the holonomy groups of the connection. I mean, that map from the isotropy groups to the diffeomorphism groups of the fiber are not injective, so it's not quite, you don't quite get the holonomy from the groupoid, from this groupoid, but the image of it is the holonomy of the connection. And then, yeah, I mean, this fiber NX, very explicitly making use of the parallel transport. Okay, so passing to the integration, so you have an algebroid associated to the connection. The isotropy Lie algebras of the algebroid are the original isotropy Lie algebras. You integrate, you start getting parallel transport of the original connection, and you start seeing the holonomy groups of the connection. And even before going to groupoids in some sense, you see these isotropy groups GXH show up. Maybe yeah. So these are the isotropic groups of GH. Right, they integrate this holonomy Lie algebra And actually, their connected component of the identity are precisely the simply connected clique groups integrating that. But they may have also more than one components. But the point is that you can play a little game, and this doesn't even require finite dimensionality. The holonomy Lie algebra may fail to be finite dimensional, but smoothness still makes sense. So you can talk about, you can associate to this Lie algebra like the resemblance of the simply connected group integrating this Lie algebra, which is a finite dimensional case. It is what I said. So just look at parts in the Lie algebra and we quotient out by smooth homotopy. And explicitly, this X on NX, and the explicit description of this action, it's simply via flows of time-dependent vector fields, right? If you take a part in this Lie algebra, it's a part of, in this Lie algebra, vector field. So it's like a time-dependent vector field on NX. You look at the associated flow, and then you take the time one diffeomorphism, and that describes the action of A on NX. And to check that it's well defined, it doesn't depend on the it only depends on the smooth homotopy class. Well, you have to check. I mean, this is not meant for you to read in detail. It just writes out the definition of homotopy. You do a little trick, and you see that it's independent of the part. But what you can notice is that the structure that is used here doesn't really use the holonomy Lie algebra. So actually, you are proving here something a bit more general. So only used, this reacts sometimes in a funny way. Or shall I do it, shall I point it there? Okay, see. So we only use that A0 and A1 are homotopic as algebraic parts. So in other words, this action is trivial on this monodromy subgroup associated to the algebroid, right? This image of, this is related to the integrability that I mentioned also in relation to Kirill's work, right? So these paths which are null homotopic as A paths, these give the monodromy subgroups. And you'll see that the action of this group actually descends modulo the image of that monodromy groups. And that's precisely how you get these isotropic groups of this groupoid. So I'm saying, if you didn't know about the groupoid, you play a bit like this, you may discover the story with the groupoids in a quite natural way. One advantage of this, as I said, is that, so maybe that's useful at some point, things make sense also in infinite, more in infinite dimensional cases. Okay, now, I was talking about the integrability of the Lie algebroid, but is it integrable? So this is the next point to address. And the answer is yes, because of a simple criteria for integrability. Let me remove it. So that's something that we learned, I think, with Rui Fernandez when we looked at integrability of Poisson manifolds. And we are proving that the existence of a complete symplectic realization of a Poisson manifold implies integrability. Actually, it's if and only if, right? So that was the hard part. And inside that proof, you see something a bit more general. So that's actually the Lie algebroid lemma theorem that underlines that argument, that if you have a Lie algebroid which has a free complete action on a submersion, then it has to be integrable. And AH was like the best one which was acting in N in a free way, and completeness was assumed from the beginning. So you see, you get integrability because of this result that we knew from the study of the integrability of Poisson manifolds. And the idea of the proof is to use the orbit foliation. Right, so this action of the algebraic on n, you can either think of it as a map between sections, so gives associates to sections vector fields, or as a bundle map from, well, really the pullback of AH to the tangent bundle of n. Right, so that's something that has an image inside here, and that's my Germanic A, by the way. The image of that gives this, what we call the orbit foliation associated to the action. And by construction, you see when you pull back the algebroid up to n, you get precisely this foliation. So the point is that this groupoid of the algebroid, if you mix it with the action and form the action groupoid, you get precisely the monodromy groupoid of the foliation. And those are always smooth, right? So foliations are always integrable. So you use the smoothness of the monodromy groupoids of foliations to deduce the smoothness of these groupoids of the algebroid. Okay, but then one realizes one can do even better, especially if you have this question like, do I find the best algebroid with x on n? I mean, the point is that the monodromy groupoid of a foliation is just one possible integration of a foliation. There are a few more. At one extreme, you have the monodromy groupoid. That's the biggest. And at the other extreme, you have the holonomy groupoid. That's the smallest. You cannot go below that without breaking smoothness. So, with this slogan of looking for integrations, which are the smallest ones, you do have one. And you do discover this concept of holonomy groupoid of the algebroid relatives to n, which in good cases has the similar property that when you take the action on n, the action groupoid on n is precisely the holonomy groupoid of the foliation. But that's not, strictly speaking, true in general. But there are many good cases in which it is. But that's somehow one of the things to take away. For an algebroid, you can talk about this canonical integration. But if it acts on a submersion, there is also a notion of holonomy groupoid relative to the submersion, to the map, to the space it acts on. And I think that we started realizing in Poisson geometry, it became more and more obvious that that's the correct notion of holonomy. For foliations, it's not so apparent because the space is there for free. So you have the holonomy without having the space. You have the space, but it's there canonically. And the actual construction of this groupoid, well, you just look at what happens for the monodromy groupoid, in which the things on the left-hand side, so you recover pi of a, you look at the monodromy groupoid of the foliation. So that's, I'm so bad with this, I don't know why. I thought I understood the basic instructions. Right, so on the right-hand side, you have leafwise paths, and you quotient out modulo leafwise homotopy. So paths in A will give you leafwise paths, and you identify them if they are homotopic there. And you can do exactly the same using holonomy. Right, so two paths in there will be identified, not if the paths, the leafwise paths are homotopic, but if they induce the same holonomy. So you quotient a bit more. And there's this groupoid, the holonomy groupoid of an algebroid relative to an A space, relative to connection. You do precisely this. So identify paths which induce the same holonomy, which in this case is parallel transport. And this we've used in Poisson geometry, for instance, building holonomy groupoids relative to simplicity realizations in our work on Poisson manifolds of compact types, in which we're relating properness of groupoids with properness of simplicity realization for isotropic simplicity realizations. So these are constructions that, yeah, we somehow they are there, they're obvious, but we had to name them, and then we realized, well, even in this classical case, it gives a bit more insight. Right, so the message is that if we want to integrate this algebroid on the action, you should not just use this monodromy groupoid, you should use the holonomy groupoid. And then the previous proposition, right, which replaces the monodromy groupoid by the holonomy groupoid, will say that this groupoid is the smallest groupoid integrating the algebroid and acting on N. And now its isotropy groups are the holonomy groups, right? So before, the isotropy were giving the holonomy, but they are not the holonomy. So now we really build the groupoid with holonomy groups, precisely the starting classical holonomy groups of the foliation. And then the story goes on in a similar way, that you can further reduce this gauge bundle of N by looking at the S fibers of the groupoid, viewing them as principal bundles, and using the action to attach the fiber. And also for the connection.
Just to clarify, the previous slide was not about transitive, right? It was general.
Certainly not for transitive. Yeah, it was general. Yeah. I mean, we used it for the cotangent bundle of a Poisson manifold, and the map was a simplicity realization. And it happened that in that case to be regular because our realization was so that they forced regularity, but it certainly was not transitive. Right. Okay, now yeah, the connection, I didn't discuss much about it. It's kind of boring from the classical. I mean, it's not boring, but it's standard. It's very standard from the classical point of view. But even the connection, one can make a couple of funny remarks. So that's something in general for any Atiyah sequence. So any transitive Lie algebroid, now it's transitive. With a splitting. So what you have for free, it's an action of A on G. So G becomes a representation of the Lie algebroid. It's just like the joint representation using the Lie bracket. Then this is a splitting of the sequence. So I put it in the right, but it's equivalent to having a splitting on the other side, on the left. So having H is equivalent to having L. So I have an L, a map from A to G available. Then there is something like a connection on the algebroid, but with values in sections of G. So it's what we call a connection relative to L. So it takes vector field sections of A and goes to gamma of G. Satisfying line is where you put in L for things to make sense. There's the explicit formula for the D. And then it satisfies some compatibility condition with the brackets, that it's pretty long. It doesn't make sense to write it here. But this is precisely what we found as the infinitesimal counterpart of multiplicative forms. So this is what we call Spencer operators in the work with Maria, Amelia Salazar, and then Francesco Catafi, and used also by Luca Cornero. So it's precisely the data that encodes a multiplicative form on the groupoid. multiplicative form or multiplicative distribution on this groupoid integrating the Lie algebroid. Now, if this Lie algebroid comes from a principal bundle, it's not very difficult to see what this form is. I mean, there are some obvious guesses, and it is what you'd guess using the pullbacks by the source and the target. But somehow the message is that it is a lot more general. So there is something going on here which is a lot more general. And if you move away from the transitive case where you lose the more classical viewpoint on connections or splittings, what will be left is these connections viewed as multiplicative forms on the groupoids. I mean, there's the final game on the groupoids. As long as they are transitive, they become principal bundle and usual stuff. If you want to do that usual stuff for things which are not transitive, already families of transitive, right, which would mean going to algebroids which are simply foliations, then you have to move to groupoids and multiplicative forms to encode these connection-like data. And then you can keep on playing now. If you learn about multiplicative structure, you start wondering. So for AH, I integrated, I have this, one of the two groupoids, let's say the relative holonomy groupoid. You end up with this one form, connection one form, multiplicative one form on the groupoid. On the other hand, N itself has the connection viewed as a subbundle. We can interpret it as a connection one form, right? So it's just the projection from Tn to the quotient of Tn by H. You can view that as a one form with coefficients whose kernel is precisely H. So if you encode a one form like that, you get a Hamiltonian-like picture, right, in which your groupoid comes with a one form, your bundle comes with a one form, and surprise, surprise, they are compatible in the multiplicative sense, right? So it's, of course, when you know this story and you are in this picture, you say, let's try to check whether we are lucky, and we are always lucky when checking this multiplicativity. So something it's, I don't think I completely understand the reasons, all the reasons for this, but it looks like we are doing the right thing in this interpretation. Right, so that's what happens when you learn about multiplicative structures. You start seeing them everywhere. Right, so I'm saying this really resembles this work that this framework that we present, that we are still working on for a general framework to handle general geometric structures that started with the thesis of Maria and then was completed for the actual structures in the thesis of Francesco, which is a different story. It's a completely different story, completely different motivation. Things just come together sometimes, at least philosophically. So in that case, we are interested in geometric structures on spaces, and geometric structures are, to talk about a geometry, you need as an input a pseudogroup of transformation which governs the geometry, right? Like Riemannian geometry, it would be about the pseudogroup of isometries in Rn. Symplectic geometry, it's about the pseudogroup of symplectic diffeomorphism, local diffeomorphism in R2n, right? And these pseudogroups are difficult to handle. There are lots of locally defined diffeomorphism. So the way to handle them is to pass to jets and form groupoids. So there are these groupoids of k-jets of deep pseudogroups. I think that if you see the notation, it you have an obvious case, that's what it is. And I mean, that's something that has been used even by Cartan, these k-jet spaces. The point is that to do an insightful theory, you need a framework which puts these on the right place. I mean, these are not just spaces. These are groupoids. They come with canonical one forms with coefficients, the so-called Cartan forms, which are well known everywhere under different names, possibly. And those Cartan forms interact nicely with the groupoid structure in the sense that they are multiplicative. So the framework that was proposed in Maria's thesis is this. So this is the main definition in her thesis. It's about Pfaffian groupoids. Groupoids with such a Pfaffian form, which is multiplicative, and it satisfies a condition, a technical condition that is important in that theory, is not satisfied by the examples that we get. But never mind about that. I mean, the basic picture is there. So these Pfaffian groupoids, that's once you have a geometry, right? So you can think of X as being Rn and gamma R local diffeomorphism, we preserve a given structure. And to talk about actual structures on manifolds, you have to look at atlases. So you do a similar construction whenever you have an atlas, a gamma atlas on a manifold M. So if I have another manifold M with an atlas S, meaning that the change of coordinates belong to this gamma. And if you take the k-jets of diffeomorphism in the atlas, you'll see you get a space on which the groupoid acts, and you also have, again, because it's jet spaces, you have these Cartan forms. And again, this can be formalized into something we generalize is the notion of G structures, which is more familiar. So they generalize into the notion of Pfaffian bundles. So you see the picture emerging. You have a Pfaffian groupoid, then you have a bundle with a one form with coefficients, an action which is multiplicative, and this PDE type of condition hidden there. But you see it's the same type of picture. So now one can go on and take that theory and apply it to the Ambrose-Singer situation and have some fun. I didn't do that, but I think there are quite a few things that can be done here. Okay, and then there is a, yeah?
The previous slide, P is N? In the previous slide.
Probably yes. P is N, yeah. P is N, sorry. Reusing some other diagrams. Actually, these reuse from my talk in the Global Poisson 2020. Just this, I reused this definition and the previous one. So I think, okay. And then there is one more, it's a cute picture that takes, it's happening at the level of N if you look at the foliations. And I think it also explains a bit the various holonomic groups that you have. I mean, you have a connection, even in the classical theory, there are all kinds of groups flying around which depend not only the point X, but points on N. And sometimes they coincide, sometimes they know they interact nicely. So actually also those show up very nicely in this picture. If you move up on N and you make use of this foliation, orbit foliation. So first of all, up there on N, you have several foliation groupoids. So that means groupoids integrate in the foliation Fa. At the two extremes, you have the one that I mentioned that you have for any foliation, the monodromy groupoid, also called pi of Fa in the previous slides, and the holonomy one. Anything else that integrates the foliation must be in between. In particular, this action groupoid that you obtain by acting with the relative holonomy on N. So these are foliation groupoids. They integrate the foliation. And one nice thing that you can do with foliation groupoids is that you can replace them by so-called Morita equivalent ones and make them étale, so discrete-like. The S fibers become discrete. But for that, you have to restrict to a complete transversal. And the nice thing here is that actually each fiber of our fiber bundle is actually a complete transversal to this foliation FA. So you can replace the whole sequence here by a Morita equivalent one just by restricting to NX. And I'm writing here what you get. I mean, this is not, I mean, you have to think what is the case. It turns out that if you restrict the monodromy groupoid to NX, you get the action groupoid for the action of the isotropy on NX. Then here, similarly, for the action of the holonomy. And here you have to effectivize the action, to force it into a more effective one. Yeah? Yes. Well, now we are back in the case of Ambrose-Singer. So I'm still, I'm in this picture. So I start with the connection. The algebroid is regular. If you're wondering more generally, I'd never, well, yeah, I don't know. I think there are many questions here that I didn't even have time to think about. It's kind of cute, and that's what I'm saying. There are things that one can try. And I think there are interesting things to discover in these, like applying what the more advanced stuff from Poisson geometry to these pictures. I think it's kind of revealing. Anyway, so these are, right, so you get these action-like groupoids, but now these are groupoids over an X. And you see, these are really Lie groupoids. These are Lie groups. But nevertheless, these are still foliation groupoids for the same infinitesimal action, but now on the fibers. But although this monodromy, although this was obtained by restricting a monodromy to a fiber, the outcome is not the monodromy groupoid. So you now have even more groupoids over NX. Next to this, you'll also have the monodromy groupoid. So I try to put everything on one diagram, having all the groupoids around, one which is monodromy, one which is holonomy, the other things in between. You have isotropy groups around. And if you dive into these, you'll start recognizing these other type of holonomy groups, variations on the holonomy groups of the foliation. But that's how they come up in this picture. So I hope you find it intriguing. And there are all kinds of variations that one can try, but somehow these, I hope this will be more useful outside the usual Ambrose-Singer. Right? It's a philosophy that applies more generally. I mean, in infinite dimensions, I mean, there are interesting examples in infinite dimension. Already we saw yesterday in the talk of Anton that using, I mean, there are two things to do in infinite dimensions. Use Banach, you are lucky. Use Fréchet, you are unlucky. Or mimic, make sense of things as they would hold morally and make them precise. So I think this last approach would work to adapt what I said also to more infinite dimensional situations. So that's one variation which in principle should work, at least partly. Then there is a germoise version of the Ambrose-Singer, Ambrose around the given section, which is like a zero section. So that it was actually for me the starting point. And this works as well. It works very nicely. The point is that in like already in Poisson geometry, right? When you look at symplectic leaves, in neighborhoods, you start getting interesting connections, but they are really local around the leaves, right? And that's, you are only interested in what happens around the leaves, so germ-wise. So if you want to use this discussion, in that case, I think it's the germoid version that works nicely without hand waving, right? So really nicely. Then, of course, there is our favorite game to play to replace TM by other algebroids. But yeah, I think that's more than a game in this case, because as I said, already when you look at parametrized Ambrose-Singer, It's replacing TM by a foliation, which topologically could be crazy. But also, if you want to allow singularities like log singularities, B singularities, I'm confused with all the terminology. But there are these nice, simple variations of TM that beg to be used also in this story. And of course, you can also use it as a theory for general A's, and I think it will relate, no, it's not, I think I know, it relates to the holonomy of A connections as was done by Rui Fernandez in his paper in Advances. Another point to make is, do I have time for this? Okay, no. So I'm gonna just say, so PDEs are formalized by these bundles with a connection. So in principle, you can use the same basic principle to find best possible groupoid acting on your bundle in order to build symmetries of PDEs. So that's a bit of a wild question, but I think it has good chances to give some interesting stuff in there. And then there is, of course, these connections that respect geometric structures along the fiber. So there is, one can, in principle, adopt the discussion. And it has been done for symplectic fibrations by Guillemin, Zimberg, Lerman, and by, for Poisson fibration, I think by at least Rui Fernandez, but also Olivier Brachic, I think. No, I think I'm going to stop here because my time is up. So I'll stop here. Thank you.
Are there more questions for Marius?
Yeah, just a stupid question on the, well, not the previous thing. So holonomy groupoids of PDEs, when you say that the PDE is formalized by connection, you really mean, you're really referring to the infinite prolongation of the PDE?
I mean to this framework, in which you start with a bundle, with Pfaffian bundles. The framework of Pfaffian bundles, when you have these, the manifold E, fibers over M, and you have this connect Pfaffian one form, satisfying the condition which, from the point of view of exterior differential systems, amounts to talking about quasi-linear Pfaffian systems. Right? I mean, it's the form in which you can put any PDE by passing to jet. So these, in practice, these are jet bundles, and this is the Cartan form. And you can talk, but that's all the structure that matters to talk about solutions, to do prolongations, to do Spencer cohomology, to do everything. So I'm just saying, if you have these, now it's, you want to put here a groupoid which acts on here, the best possible one. So it looks like it fits in this philosophy. Of course, I'm putting it in a very simplistic way because you'll analyze it with jet spaces and so on, and you look at the algebroid first. But I think there may be something there to make sense of a Galois group of the PDE.
And how about going to the infinite jet and really having a connection?
That's what I said. It may be more involved. You have to put jets in. You can do that as well. Some things will become apparently sleep. I mean, it's the kind of thing that you say, oh, very nice, it's involutive, and then what can I do with it? Nothing.
Right.
Well, you can do the formal geometry. It's not true. I'm exaggerating. But as long as you want to do parallel transport and holonomy transport, which is important in this story, you are dead. The ODEs will not give you anything. So it's to be tried. Are there students? We have some master students from Utrecht that may be interested in having worked for a couple of years.
Thanks, Marius, for the inspiring talk. Since you tell us about the general criteria, this lemma on integrability, And we are remembering also Mackenzie. I just wanted to mention that recently Daniel Alvarez published an alternative proof for this criterion from a global setting, like using double structures and Mackenzie, no? Vacant groups, etc. I just want to mention this.
Yeah, I wasn't aware of that. Thanks. Yeah, I think there are various people here have done work that touches upon the discussion here. Also, the existence of complete Ehrenschmann connections. Now I remember, right, that they always exist in this locally trivial fibration. I think there was all kinds of proofs with mistakes, and it was Matias and Rui Fernandez that found a nice proof, again inspired by some work on Poisson geometry and groupoids.
I think. Hi, Marius. Thank you
Hi.
very much for the nice talk. Could you, you just mentioned I guess this is a general setup, well, sort of a general setup that you can apply in many concrete situations, this N thingy. You just mentioned you could apply to what Poisson. Could you mention more precisely some examples you could apply this theory of about this situation of N?
Well, I said we did apply it. We did use implicity in various stuff we did in Poisson geometry when N to M was a simplicity realization.
Simplicity realization.
Or when N was a normal bundle over the leaf and M was becoming a symplectic leaf.
I see.
And you could also apply it in other instances, I'm saying, for different N's.
Right, I guess it's...
I mean, for like
Generating.
symplectic fibrations, there is an entire discussion, an obvious N there, which is the symplectic vibration itself, to test all of these and to hopefully recover what's, well, I think you do recover. It's more, the symplectic vibration has more interesting stuff around, and that we can embed in this discussion.
Okay.
I don't know, if you give me 5 minutes, I'll enlarge the list
You
of
probably
examples.
have a
But I think
list.
there is plenty of possibilities.
I guess. Wonderful work. Thank you.
Okay, that was very interesting. Could I ask a question about original Ambrose-Singer? So if you have a manifold with special holonomy on the tangent bundle, let's say you have a Riemannian manifold, special holonomy on the tangent bundle, what you're saying is that you can construct a groupoid, a holonomy groupoid, which acts on the tangent bundle via all the holonomies, right?
Yep.
So my question is, what other structure do you get besides the Pfaffian form on this groupoid? Is there anything else that reflects the Riemannian geometry, or?
Yeah, that's a good point. I think the Pfaffian form encodes more than what you may expect, but I think it's not everything, right? So this ambiguous last line here, when you have the connection that disperse certain geometric structures, like in the case of symplectic fibrations, where you have symplectic structure on the fiber, and there is more to the story. So it's not that, I mean, I have to think now, okay, what if I have geometric structures and try to figure out whether there is a more to the story in full generality. Right now, I would say, no, you have to work case by case to see what more is there, but for sure there is something more. And it's not...
But in cases that you have investigated, is there have you seen more than the Pfaffian form?
I mean, yeah, I think what has been done for symplectic fibrations and for Poisson fibrations, it goes in the direction of Hamiltonian fibrations in relation with the existence of a global closed-2 form, which tames all the symplectic structure of the fibers, and then, yeah, that's where there is extra structure and things. But I don't know how to make that part of a general story, so that's why it's my last bullet here. But it will be interesting. Also, I didn't have time to think about it, so students.
Anything else? Okay, there is a question in chat.
So there are two comments by Rui Fernandez. The first one is that for A connections, he says that there's an Ambrose-Singer theorem in his paper in Advances. This is the first comment. And
yeah,
then
I think that's what I was trying to hint here, this holonomy for I connections. Yeah.
so the second one is that the multiplicative point of view seems more natural for the generalization proposed by Joan Marcoux and Rui Fernandez, that they call multiplicative Ehresmann connections in IM Ehresmann connections for surjective submersive morphisms of groupoids and algebroids. And this is a recent preprint. This is the comment by Rui in the chat.
Good. I have to look at their paper. I think this, I mean, the start point of this, no, the core of this, what I was talking about here, was prepared as a paper in honor of, for the volume in honor of Kirill, which I think was really before I've seen the talks of Yonuts and Rui. So it's left in that stage. I never finished it, so that's why I never submitted it. So I thought this would be a good opportunity. But yeah, I'm aware they've done some work meanwhile. I still have to study. So it's good we are all here. No, he still has to come here. So come here, Rui.
Okay, let's thank the speaker again.
Thank you.
And now I believe we have a coffee break.